Now we are going to start with the oxidation state and trends in chemical reactivity in the 13th group. That means we are going to see that what kind of oxidation states they show and what kind of trends in chemical reactivity, or the basic feature what exists which is responsible for the chemical reactivity, what is its actual trend. So as you all know that the 13th group is boron, aluminium, gallium, indium and thallium. You know that we have already discussed the electronic configuration and the physical properties as well. So if we talk about its oxidation state, then we have seen that because we know their electronic configuration is Ns2 Np1. That means they have 3 electrons in total in their valence shell, 2 in S and 1 in P. So what happened, like if we consider that what number of electrons are going to participate in the bond formation, so we know that in P block the group oxidation state is equal to the electrons in the S, that is 2, and electron in the P of the valence shell. So that means the group oxidation state is +3. Right, that means if we count S and P electrons both, the group oxidation state is going to be +3. So if we see that how many elements out of this group actually show the +3 oxidation state, so we'll see that boron, aluminium, they generally show only group oxidation state, right? But as we move down, they are showing their group oxidation state also, but in addition to it, they are showing +1 oxidation state also. We discussed before also that in the general properties of P block, that for the for 13, 14 and 15 group, that means for the boron family, carbon family and the nitrogen family, what we see that the group oxidation state is stable for the lighter elements, but as we move down, as we come across the heavier element, the oxidation state, which is you can say that 2 unit less than their group oxidation state, is more stable. So this we have seen here, that as we are moving down, the 2 unit less means +1, that means for heavier elements +1 oxidation state is generally stable, that means it is becoming more stable. Though they are showing +3 also, but in addition to that they are showing +1 oxidation state also. And for thallium if we talk about, then out of +3 and +1, its more stable oxidation state is +1 because it is heaviest of all in the 13 group. And what is the reason behind? We know that we have already discussed when we were discussing the general properties of P block, that is the inert pair effect. I'll just recall in a short span, because we have already done this. What happens as we move down, we know that filling of D and F orbitals are taking place. The filling of D and F orbitals are taking place. So due to which we also know that they show poor shielding effect. What they do? They show poor shielding effect. And due to this poor shielding effect, the nuclear charge increases, because the effective nuclear charge is not less, it is actually more. That means the nucleus is attracting its valence shell more tightly. The electrons present in valence shell are more tightly attracted by the nucleus. The reason being that is due to filling of D and F orbitals, they have poor shielding effect. And what is the reason that they show poor shielding effect? Because they are big in size, or you can say they are diffuse shape actually. Their diffuse shape make them show poor shielding effect, due to which nuclear charge increase. That means the valence shell electrons are tightly held by the nucleus, due to which you can say that as we move down, because we know that number of electrons in D and F are increasing. So that means the poor shielding effect is actually increasing as we move down. So that means the nuclear charge is becoming more and more as we are moving down, because the number of electrons are increasing in D and F. So you can say that the amount of nuclear charge is increasing as we are moving down. So due to increase in nuclear charge, what happened? The nucleus actually hold these S electrons more tightly. So it doesn't allow these S orbital electrons to participate in bond formation. So what we are left with, if it will not participate, obviously we are left with only electrons in the P orbital. So only this is going to participate. So we are going to minus these S electrons from the group oxidation state. So as you know, the group oxidation state is +3. So when you minus this 2 electrons, that is the of S orbital which is held tightly, so that means our oxidation state which will be more stable will be +1. So this is inert pair effect. So if somebody is going to ask you, you are going to write a general definition for the inert pair effect, that is the reluctance in the participation of s electrons in the bond formation due to poor shielding effect and due to increased nuclear charge. The s orbital electrons do not participate in bond formation, and that is the reason that as we move down, the 2 unit less than the group oxidation state become more stable for the heavier elements. And it is seen maximum for the heavier ones, because the heavier ones have more DNF filling, so that means they are showing the poorest shielding effect, and therefore the nuclear charge is actually more in them. So that is the reason these electrons are held more tightly. So this is the reason, I think you got it, that though they show the +3 oxidation state, but for the heavier, the +1 oxidation state becomes more stable. So as you can see, gallium, indium, thallium, both are, all three of them are showing +1 and +3, but the stable one for thallium is +1. But if we talk about gallium, then +3 is more stable than comparatively +1. So actually this kind of you can say variation you get to see in the p block, that is in this boron family. So now let us talk about trends in chemical reactivity. So as you know, again the configuration we have already discussed is Ns2Np1, the general one. So that means this group is going to participate 2 electrons from s orbital and 1 from p orbital in the bond formation. That means in total they are going to use their 3 electrons in the bond formation. Except thallium, we see that except thallium, all of them actually they make use of all these 3 electrons, but thallium doesn't actually make use of all its 3 electrons, the reason being the inert pair effect we have already discussed. So what happened is that you know that in the 13th group the 3 electron participation is more favored. The reason being because when they make use of 3 electrons, after that what actually happen in them, that they form an ion with 3 positive charge, right? When they become 3 positive, when they become charged with 3 positive, that means they become very small. They become very small, and according to the Fezan rule we done in the chemical bonding, that smaller is the size of the cation. It is cation, right? Because the atom with positive charge is called as cation. So 3 positive means a bigger charge, so that means cation will be very small, and we have discussed according to Fezan rule in chemical bonding that more smaller is the cation, then more polarizing power it has. So that means it is going to have more polarizing power, and more polarizing power favor covalent bonding. So this is the reason that they actually favor the formation of 3 positive, that means, or you can say they make use of 3 electrons in the bond formation. So got it, the first point. The second thing is that if these metals try to become M3 positive, that means they will need to lose 3 electrons. That means first ionization energy, let's say for removing 1 electron, second for removing 2 second electron, third for removing third electron. So in total we are going to add them. So their sum actually becomes very high, that this much energy cannot be supplied to them in order to make them form M3 positive. That is the reason that they show maximum covalent bonding. They do not form ionic bond, they form covalent bond. They make use of 3 electrons, but in the formation of covalent bond, not the ionic, because for some of the elements we will discuss now of this family, actually converting the metal into M3 positive require higher energy, and that much energy is not available that it can form M3 positive. That means it loses 3 electrons. So this loss becomes actually very difficult due to increased ionization energy. Third reason is that you have seen that the one which show ionic bonding, right, like we know metals and non-metals show this kind of bonding, ionic bonding, because they have a high electronegativity difference in them, right? They have high electronegativity difference. That means because we know metals are present extreme left, so they are bigger. Non-metals are present extreme right, they are smaller. So we know that smaller the size, more is the electronegativity, bigger is the size, less is the electronegativity. So we can say that there is a huge difference of electronegativity between them. and there is a condition that there has to be electronegativity difference for the formation of ionic bond. But if we talk about this 13 group, they are electronegative. They are quite electronegative. So suppose if I take a member of this, let's say we take a member of this family, let's say boron, and I take some of other member, let us say that Cl, I take chlorine from 17 group. So this is a member of 13 and this is a member of 17, right? So they don't have that much of electronegativity difference that the ionic bond is favored. So instead of forming the ionic bond, what they'll do is they will show a covalent bonding, because for the formation of ionic bond there has to be electronegativity difference, a large electronegativity difference, and because they are quite electronegative, so that much difference is not observed when they combine with some other element. Got it? So you need to know that what is the reason that 13 group elements mainly, except thallium, keep in mind, except thallium, the other members actually make use of 3 electrons, but they are not losing those 3 electrons. Rather, they are just sharing with some other element in order to form a covalent bond. And this can be asked to you that why the covalent bonding is favored in the 13 group. So what you need to do is, you need to answer in a way that they make use of 3 electrons, they show covalent bonding. The reason these 3, that is that we know that by making use of 3 electrons they become quite smaller, and smaller means they have high polarizing power. High polarizing power means more covalent character. Second, for forming metal into M3 positive requires sum of 3 ionization energy. The sum is quite high and we cannot supply them, so converting them into M3 positive is quite difficult. Third, for the formation of ionic bond, what is needed is that there has to be a large electronegativity difference. As we know that they belong to a 13 group, so they are quite electronegative. So when they combine with some other element, we don't observe that kind of electronegativity difference. So that is the reason they form covalent bonding, right? Now, if we talk about the members of this family again, so we have seen that the boron under any condition, right, do not lose 3 electrons and do not form this 3 positive, right. So that means boron can never form an ionic bond. The reason being because we know that it is the first member, so that means it will be small, right. So because it is very small, so obviously its ionization energy is quite high. So obviously to remove 3 electrons we will require much energy, and that energy cannot be supplied. So in any condition boron never show ionic bonding, it always shows a covalent bonding because it is smaller, so obviously it will be having a high polarizing power. And moreover you need to answer, like if you get a question that boron never form B3 positive, so you or you can be asked that boron always show covalent bonding. The question can be in any form. So you are going to answer in a way that boron cannot lose its 3 electrons because it is smaller, so the ionization energy is quite high and we cannot supply that energy in order to convert it into B3 positive. So that is the reason it shows covalent bonding instead of showing the ionic bond. And if we talk about the next member to boron, that is aluminium, so we will see that aluminium can form ionic bonding or can show ionic bonding also, as well as it can show a covalent bonding also. Example, suppose AlF3, in this the aluminium is showing an ionic bond because there is a quite electronegativity difference between 2. Likewise, if we talk about the best fertilizer, as we have already discussed, that is the aluminium sulfate. In that also we see an ionic bonding. But if you talk about AlCl3, AlBr3, that means aluminium halides except AlF3, they are all covalent in nature. That means they are forming a covalent bond. And we have seen that if we talk about gallium, indium and thallium, then what they do is, I'll write here, gallium, indium and thallium, they show mostly covalent bonding, right, when in anhydrous condition. That means when there is no solution or no water or no liquid present. But whenever they are present in a solution form, then they show ionic bonding. The reason in this even the aluminium is included, right. The reason being because they are smaller in size, so what happened when we conduct the reaction in solution, they get hydrated to a great extent. And when they get hydrated to a great extent, we know they will be releasing more hydration energy. This energy is actually utilized for converting the metal, that is these metals, into, that means they can lose their electrons and they can convert into M3 positive. So this is an important thing you need to remember, that except boron, aluminium, gallium, indium and thallium, that is the 4 members except the boron, in the solution form they show a kind of ionic bonding. The reason being because when they are in solution form they get hydrated to a good extent, and whenever they get hydrated to a good extent, that means they are going to release more hydration energy, and that energy actually compensates that huge ionization energy which is required in order to lose 3 electrons. So that means the formation of M3 positive is actually favored, but only when they are present in a solution form. But if we talk about the thallium, what we see is that in case of thallium, I'll write here, we know that for it +1 oxidation state is more stable, right? So that means what it can do is, like when it is present in +1 oxidation state, it is going to show an ionic bonding. So you need to remember, boron always show covalent bonding. The reason being it requires high energy and that is not available to provided that it can lose 3 electrons. Aluminium can show both, right? Ionic and covalent, we have already mentioned the formulas for the compounds. Aluminium, gallium, indium and thallium in solution form, they can lose electrons because they get hydrated to maximum extent, release a good amount of energy which is actually compensated. That means that can be used in order to lose 3 electrons. But if we talk about thallium in +1 oxidation state, it is going to show a bonding, that is the ionic bond. So this is actually, you need to be familiar that when they are going to show an ionic bond, in which oxidation state they are going to show a covalent bonding. And another important feature what we have seen, that in the boron family, whenever they are present, like I am talking about all the members of the family, whenever they are in +3 oxidation state, like if I take an example of BCl3, then what we observe actually, that they act as Lewis acids. They act as Lewis acids. Why? You know that Lewis acids are those which are actually deficient in number of electrons, and as you can see in this figure, it is surrounded by 3 bonds, 3 single bonds with chlorine. That means 2 electrons, 4 and 6. So that means boron is having only 6 electrons in valence shell. That means we know that every atom need to complete its octet. So that means 8 electrons are not here, only 6 electrons are present. So that means it is in actually need of electrons, it actually need 2 electrons in order to complete its octet. That is why we can say that it is an electron deficient compound. That means it is actually in need of electrons because the central atom octet is not complete, and you can easily see that it has only 6 electrons around. So it is lacking 2 electrons, needs 2 electrons to complete its octet. So we can say that it is an electrodeficient compound. So this is not seen only in case of boron. I am talking about all the members, that whenever they are present in a +3 oxidation state, that means trivalent oxidation state, at that time they act as an electron deficient compound because the octet of the central atom is incomplete, it needs an electron. So let's say that if BCl3 is like this, so it is an electron deficient. So obviously it acts as Lewis acids. We know that the compounds or any ions which need electron, they act as Lewis acids. We have already discussed in the equilibrium chapter also. So if I react with any Lewis base, let us say I react with NH3, right? We know that NH3 has a lone pair. So that means it can actually donate its lone pair to boron, right, by a coordinate bond, and now the octet is complete and even this is stable. So what kind of bonding is this? This is a coordinate bond. You know that whenever a bond is formed between Lewis acid and Lewis base, it is a coordinate bond because here the electrons are contributed only by one compound and the other is actually deficient in the electrons. So means we don't need to focus actually on this. You just need to be familiar that all the boron compounds in trivalent state, they act as Lewis acids. That means they need electron. So they are electron deficient compounds. And if we see the Lewis acidic character, we will see that it decreases down the group. That means if we have BX3, ALX3, I am making halides of all them. So we have gallium halide, we have indium halide, we have thallium halide. So it is going to be more acidic, it is less, more less and more less. So that means as the size of the, you can say that as the size of element is increasing, the Lewis acidic character is actually decreasing. So you need to remember that. And definitely you need to remember this also, that whenever they are present in a trivalent oxidation state, they behave as Lewis acids, right. So this is the general trend about the oxidation state and trends in chemical reactivity. So now let us start their reaction with air, water, right. That means we are starting with the chemical properties now.